Hello, everyone, and welcome to our live webinar today on selecting the right 3D printing material. I'd like to introduce myself. I'm Serena, and I'm on the marketing team here at Xometry. A couple of quick notes before we get started. Please submit your questions throughout the webinar for Greg to answer at the end. I'll be monitoring the questions in our question bank, so please submit them at any time. We'll also send a webinar recording around for anyone who'd like a copy, and so you can share it with your colleagues. And be sure to stick around until the end of the webinar for a special discount code for all of our webinar attendees. So next, I'd like to introduce our presenter, Greg Paulsen. He is the Director of Applications Engineering here at Xometry. He brings many years of experience and leadership to our team here and is an expert panelist and speaker on all things additive manufacturing. You may have seen some of the engineering challenges videos he's been in. So he is the star of the Will It series. Before Xometry, he was a project engineer for many years doing rapid prototyping, so he brings both subject matter expertise as well as manufacturability expertise. So thanks again for tuning in, and don't forget to submit your questions as we go along. With that, I'll pass it over to Greg.
Hey, Serena, and thank you so much for the introduction. And as Serena said, it is so important. I work best with that Q&A period. So along the way, if you have any questions, please submit them. We'll address as many as we can at the end, but that's honestly my favorite part about talking about this. I've been talking for the last decade on additive manufacturing. I've had a unique role where I'm not just in the academics of it, I'm actually using it. So what I work best in is when things are actually, like literally the rubber is hitting the road, when things are actually applied. So today we are talking materials, specifically additive manufacturing materials. To get started here, I do want to make sure that you guys know who we are and what Xometry is. So I'm going to go and talk about our business model very briefly, talk about a little bit of the new features that we have on our website, and then we're going to dive deep into why materials matter, talk about some specific application examples, and go over some additional resources, and then of course the Q&A at the end. So for those of you who are current customers and for those of you who are new, I just love talking Xometry's business model because it's a really unique experience. I've been in both the buyer and supplier seat, and what Xometry brings to the table is it eliminates that whole RFQ process. You put all your files together, you wait 5-6 days. Sometimes you get responses that you don't need. We actually inject data science, AI learning, and a slick interface to give you instant online pricing and an e-commerce type of checkout system. So it's almost bringing that Amazon.com experience to custom manufacturing. We do this by having our single site for many manufacturing processes and a fulfillment side, which is a large network of over 2,500 small business manufacturers. And these manufacturers are specialized in CNC machining, sheet metal, additive manufacturing, injection molding. And what we're able to do is pair your projects and its needs with those best able to produce that. That gets you better pricing. That also gets you better quality of the work. And just kind of showing you a distribution map here, we have different manufacturers in different sectors. And so you're working on medical device, aerospace, tech, energy, consumer electronics. We have the right shop in our system for you, and we do that matchmaking just at a click of a button. So let's show you what the site looks like. And what you're going to see is actually newer. Probably, I think last week we did an update, so you may see a little bit of a different interface than what you're used to. But of course, this is Xometry's website. Before I go to the quoting engine, I do want to show that we have some really great resources here. I'll talk about those at the end, but a lot of this is stuff that myself or our expert team has written to help you to choose the right process. So check out our design guides, our FAQ, our videos as well. And you can take a look at different capabilities that we have on our site. So look at our site as a knowledge resource, not just a service. So let's get a quote. So our quoting starts with 3D CAD models. I'm going to upload something from our site, but just to tell you how quick this is. So this used to be, again, a multi-day process. is now at a click of a button. I'm going to do this drone link here, click and go, and that's it. That's your pricing. So as soon as the CAD file is interpreted, we provide pricing in all our manufacturing processes. You can see here the new interface. So this is what's new is we have our standard and expedite that are available right here, as well as like just a very transparent view, as well as this is something that we're experimenting with, which is an economy option that some of you may already see on the website. So beyond things like different certifications, so if you need COC, hardware traceability, say you need like a DFARS compliant material that's typically for CNC machining, or if you're ITAR, it's a click of a button away, and we have multiple manufacturing processes. Today I'm going to be talking 3D printing, but it's just very nice to see that you can compare between different parts all at once, or different manufacturing technologies. Let's say I want to make 17 of these. Put that in, price automatically updates. You can see some economy of scale here. With this, it's actually based SLS nylon right now, but you can quickly move between different processes. And so let's say this is motion fusion. You can go and see your price update right away. So I'll go a little bit further into this when I'm talking about materials, but I did want to show you how slick our interface is with this with our website. And again, you can go between CNC machining, urethane casting, and all these different 3D processes like motion fusion, FDM, DMLS, etc. We have, again, we have these industrial manufacturing capabilities, CNC machining, sheet metal fabrication, plastic, metal 3D printing, urethane casting, injection molding, and we're also doing things like metal, plastic extrusion, die casting, metal stamping that we're starting to look into as well. We're going to move into why does material matter? And again, my focus today is on 3D printing materials. So here's first the importance. There's no one size fits all material. If there was, that's all we'd be selling. And I would love it, actually. It'd make life a lot easier on the decisions that we have to make. But different materials have different properties. They live in different environments. They have different needs that they fill. Materials, depending on what you're choosing, can increase the efficiency of the parts production, whether that's the actual material that dictates what process is used, or if it's a material that may have a different cure time, or but material that that just allows you a higher throughput, so it's something maybe more available. That stuff is hand in hand with cost efficiency. What's my economy of scale here? Am I doing this part once? I just need it to function one time around, or am I making this multiple times? And I want to make sure that my first order of 2 is just the same quality as my next 3 orders of 550. And so there's different processes, different materials, especially in 3D printing, that are going to give me that that cost efficiency and that repeatability. And the other thing that I want to note is my background is strengths and trade-offs. With 3D printing, you are here to match materials to the application. So we are looking at a limited list compared to other technologies that are more established, like machining or injection molding. For sure, injection molding, you have thousands and thousands of materials. So a lot of times, what I'm trying to listen to is between the lines. How's this part going to be functioning? Where's it going to live? You know, what's going to help me build that decision? And for me, like my mental model usually puts me in these 6 categories. So, you know, where's this part going to be? It's going to be bolted to the underside of a car where it has to live in -40 to 140 degree environment, being splashed up with gasoline, mud, you name it. Or is it going to be something that's going to be hanging out in my kitchen? You know, so let me know a little bit about where that part's going to live. It's going to help me determine some specific needs of the materials. Do I have a cost constraint? Talking about that scale, like, am I trying to sell this product for $32 on Amazon? If so, then I may actually be limited based off geometry and function on different materials because they may break my margin. Cosmetics. I'll touch base on this even deeper in the next few slides here, but it is so important to many of our clients, and cosmetics usually leads me down a certain category of 3D printing processes and therefore certain category materials. Design functions, clips, snap features. Is this thing going to be need to be screwed and unscrewed? Am I going to actually need to install something to it? This is going to be something that's going to help me understand the material requirements. Environments doesn't be static dissipative, flame retardant. Doesn't need to live in temperatures above boiling all the time. Regulatory compliances. Do I need to do something like sterilize this part? Am I looking for something that's the food safe is actually more of an application, but I need something that I need to make food safe. Am I taking this to FDA trials? It will definitely select me down, especially when you say FDA or something like that. I'm going to start narrowing that down to probably 3 or 4 material categories. It's going to because I know they are tried and true, and they have been pushed through the same trials before. So, cosmetics. One of the easiest things to down select for me is when your needs are, I am looking to display something that is show quality. I'm going to start moving towards that smoother surface finish. If you're looking for something that's larger or macro and to demonstrate a specific material, I may be okay with something with coarser layer lines, and they all have their different benefits. But just something to understand, and something from our customer feedback that we see all the time, is knowing what the surface finishes is one of the most important things about the materials, because it's not just the material itself, but it's the process in which that material was the part was formed. So FDM is a layer by layer process. It is building something with an extruded filament. You have those significant step layer lines, usually 10,000ths of an inch. If you have a larger part like that's over 14 inches in a dimension, you may see 13,000ths of an inch layers. Selective laser sintering, multi-jet fusion have this kind of middle range, general use matte, almost like sugar cube finish to it. You can use some things like media tumble SLS, but overall you should expect that anywhere from that sugar cube to eggshell to the touch. These photopolymers, stereolithography, polyjet, they create parts that have a smoother to touch finish. So that's going to be that smoother than eggshell. And these can also be easily sanded and post-finished to bring it to an even smoother state. And kind of segueing into that is the other easy down select for me on choosing my material, which is clarity. So when someone says, I want a clear part, I usually will frame you and say that every one of our clear materials that I have listed at the bottom here, so rigid clear from Polyjet or SLA's Clear View, Accura 60, Somos Water Clear, Watershed, those materials are inherently clear like an ice cube, but understand that the surface itself will have a matte look as a standard finish. So understand that if you are looking to build more transparency with SLA, sometimes you could go to more of a natural or what we call a strip and chip finish, which is we touch it as low as possible. That means usually the naturally grown finish or surfaces, the ones that don't have support structures, have a decent clarity. Again, think ice cube, don't think magnifying glass or window pane, but it helps bring you closer to there. But if you want to do something that it looks more like this face mask on this side, you're talking about somewhere around $800 to $1,000 of labor. This is essentially polishing your headlights on steroids. So you're taking a part that comes out inherently frosted, on the inside is clear through, and you're doing a full surface treatment, often with clear coats and different hand finishes, moving from maybe like a 400 to 600 to 800 to 1200 to 1800 to 2200 to 2600 wet sand to bring that grit down to get a high polish out of it. So just understand that when you say gloss and clear, what the actual ask is asking for manual labor into that. And that may affect, if you require parts in scale, it may affect the decisions that you're looking to make, because labor doesn't scale as well as, for example, just the part production itself. The other quick down selects that I have for choosing the right material, if you ask for rubber-like, right now we have a prototyping material through Polyjet that'll bring you to a short A27 to short A95. So if you're not familiar with short values, the lower the short value is, the more compressible it is. So short A27 is kind of like chewing gum. Short A95 is going to bring you up to something that kind of feels like a road tire. And so short A50, kind of in the middle, 50 and 60, is going to be feel more like squeezing into a rubber band. Just understand that durometer, which is these shore levels, is actually the measurement of the squish. It's not the measurement of the stretch. So this is really good for touch-like prototypes, but if you are or things like gaskets where you need some compression, but if you are prototyping rubber-like to exhibit a stretch, polyjet does not have the same elasticity that a rubber band or a silicone wrap would have. So just understand that it does tend to tear when it's being stretched, if you're assuming that's going to stretch like a rubber band. Metals are the other easy down select because there's essentially one main process right now that is making metal parts. And we can build it in 17 fours, 316 aluminum alloy. The process is called direct metal laser sintering. And the part on the right here is an example of that, where you can build a conformal part. And this part's actually really cool. If you looked on the other side, it has about 30 different channels that all start from the center channel here. So you can do some really unique 3D printed driven geometries out of metal, but just understand that it's limited in what metals you can use in the build size. We can also do some things. So if you're talking about something that needs to have metallic, or maybe it's metallic because it has an EMI requirement, we can nickel plate materials like SLS nylon. And what it does is it does offer mechanical stiffness, so it makes it about 5x stiffer. And also it does have some EMI shielding effects as well. So I usually see that used for both of those. But just understand that it's not a chrome plate. It's not a cosmetic look. It is something that is a matte mechanical function, or adds a matte nickel plate finish to give it a more mechanical attribute. So this is where we start getting to the nitty gritty. So we talked about rubbers, about one process chain does that. Metals, about one process chain does that. And when I'm talking about cosmetics, I'm usually going to lean you towards these photopolymers. When we talk thermoplastics, it's going to start bringing me into more mechanical properties. That doesn't mean that photopolymers can't act in that way. It just means that thermoplastics tend to have higher resilience under mechanical stress. So SLS, multi-jet fusion, and FDM builds parts in thermoplastics. One of the main characteristics is it's much more impact resistance than a photopolymer. In fact, nylon, usually when someone's asking me for something that's impact resistant, I'm going to bring you towards nylon. It's a very popular material for 3D printing, but it's also highly resilient to drops. Kind of, you accidentally drop it and it falls between a car door or something. It's not going to snap on you. It usually pops back into shape. We have materials like Ultem and FDM that are specifically designed to be in extreme environments, including high heat. So Ultem is usually the highly heat resistant material that I'll lean you towards if you bring up those requirements. If you're looking for chemical resistance, for example, ABS is not resistant to acetone, and that's why you could smooth ABS with acetone, is because literally it's actually degrading the material on the outside to create a slick surface. But you can choose other materials like nylon or even Ultem, and it will actually be more resilient to these. So depending on what chemistries you're looking for, the beautiful thing about this is these are thermoplastics. The families are not special in themselves, so you can actually look at a standard chemical compatibility chart and usually figure out which materials work best for you by the material category. Some of these materials, like nylon, Ultem, ABS M30I, can be sterilized. We have a type of polycarbonate, PCISO, that can be sterilized. So if you do have that requirement, we do have a few materials for you. Going back to the other most common down select for me is saying, I have clips, I have snaps. I'm going to start looking to this more ductile materials again, like nylon. So on the opposite side, we have polycarbonate, ABS, ASA. They are general purpose. They are stiff materials. In fact, polycarbonate, I've actually moved polycarbonate or moved CNC aluminum parts to polycarbonate at times to get a better cost saving and just-in-time manufacturability for certain customers, because what they needed was something that remained stiff and fixture parts together, but they also didn't want to have the high-end costs of CNC machining. When we talk SLA, something to note is we have high amounts of materials and they're engineered to act like a material. So they may not have the heat resistance of ABS, but they may have the mechanical action like ABS does, or they may not have the chemical compatibility of one material, but they may get you the surface finish of polypropylene, or they may give you that flex. So just understand that we categorize on Xometry our SLA by what they act like. So whether it's polypropylene, ABS, polycarbonate, or we have an extremely stiff material, our application engineer likes to say, don't think plastic, think toilet bowl with our ceramic filled accurate bluestone. So just understand that SLA is more of a many materials engineered to act like, and where PolyJet tends to have a single material that can be manipulated digitally to give it different properties. And of course, metals are metal. They're fully dense, durable, and they are end use. So I'm going to spend this time talking more about how these parts are made and about specific examples to kind of get your mind thinking. And again, this is a good reminder to start asking some questions and adding them to the list, because we'll be addressing them at the end of this presentation. So in plastic 3D printing, we have 3 different processes: SLS, multi-jet fusion, and FDM. SLS and multi-jet fusion both build parts in nylon and have very similar traits to them as far as what they are, what they're useful for. And that's because multi-jet fusion is actually an evolution of what SLS is. So SLS has been around for quite a bit, going on about 3 decades now. And it's used for heavy applications in prototyping and low volume production. It builds parts in a nylon powder bed without the need for support structure. You could stack parts in the X, Y, and Z direction and literally float them in your build. So you have a high throughput for this. It also makes the per part price cheap, and it makes the throughput, like the lead times usually are pretty quick, like starting at about 3 business days or so. You can see that matte grainy finish like we talked about, and you're also looking at a pretty good detail resolution, not super crisp on small features, but pretty good for the most part. So SLS is kind of my 85% tool. 85% of the time when I'm looking at a 3D printing project, I probably will start with SLS nylon. Other thing to talk about is HP multi-jet fusion. So this builds with a very similar material. In fact, it's almost the identical material. It's of nylon for nylon 12 that SLS does, but it fuses in a different way. It actually inks across the cross section of the parts. Has an edging compound to hold the heat in, and a heat bar will go, and essentially where it's inked, it'll generate enough heat to sinter those materials. So it's a different way of sintering nylon. I tend to find it has a little bit better feature properties when you have parts with flex to them, especially repeated flex. But just note that all these parts here are dyed black multi-jet fusion. It comes in a kind of a matte gray natural look, and you can dye it black. But because it's gray, you can't do things like dye it red or dye it yellow like you can with SLS nylon. FDM, probably very common if you're used to seeing desktop printers. You're going to see that spool of filament being deposited through. FDM is a boutique manufacturing where SLS and MJF are both using nylon material and this generically good material and building a lot of parts at once. FDM is usually building a few parts in whatever specific engineered material you're looking for. So we have a large variety of materials, and we're usually running them in small batches. So if you look at Xometry, in our network, we tend to have an army of FDM machines where we have much fewer MJF and SLS machines for producing parts because they have a single material and a higher throughput. So think designing for CNC machining. This favors the bulky. It's a very stable material at very large sizes, up to 36 inches. You can get qualified materials like Ultim built in this. We have PCABS. We have other materials. So it has a high variety of engineered materials. But just understand that because it's layer by layer, cosmetically, it's probably the least appealing of these processes. It can still look great. Don't get me wrong. Like this part here in polycarbonate, all these concentric features look absolutely excellent. But you can see on parts that have gradual contours, you're going to see that stair stepping. So let's talk about real applications here. We've had a customer, and they've actually moved to injection molding on this project. But just talking about their iterative prototyping needs. So they're making these archery tuning forks. They want to prototype a product that can flex over a bow frame and snap into place. So this image here, you can see how it snaps in place. It's pretty cool. It actually, I don't know much about archery, but they're checking the torsion. So how much are you flexing the bow in a direction left or right versus just pulling straight back? And it'll actually help you train better as an archer. So this part needs to be put on and off the bow every single time it's being used. So can it flex, snap, can you repeat it? So I'm going to be looking at ductility. And they're also looking for many iterations. I mean, just look at this picture here. You can see this is not just one order. This is orders over the years. So they're looking for something that's more economical. You'll also see in this picture, I think, with my guess here, everything that you see here is SLS nylon. So, and that was what I would choose as well in this application. So SLS nylon is cheap at the quantity 1 level. It has that ductility. It's very good for high iteration where you can shotgun approach. You can put 5 parts on your quote with different configurations, press order, and you have the similar discounts as if you just made 1 part quantity 5. So SLS just says, give me all the parts you need, and I'll be cheap for you. Multi-jet fusion would be my second choice, again for the same reasons as SLS. Just understand that multi-jet fusion scales better over higher quantities, but at quantity 1 is going to be a higher price than SLS. That's why I go from double dollar signs to single dollar signs. FDM nylon 12. This is a great profile, like a single cross section extruded up. So I can use FDM well in this. I'd be worried for FDM if this part had, for example, the tuning fork perpendicular to this line, because then there's going to be some weak spots on that Z layer as I build the parts from bottom to top with extruded filament. Because it has a single profile going from bottom to top, nylon 12 works really well, but it may not be necessary because we have these other less expensive options for nylon 12. PCABS would be the 4th choice that I have here, and again, because it has a decent amount of stiffness and flexibility, and that's also an FDM material. So I really like this application, and I like it even better because we actually helped this customer move to injection molding, and we've actually done production runs of this part for injection molding. So they were able to take a part fully from iterative prototype sampling to full production through Xometry. Another great example that we have here, and this is something that I see very often for FDM, is these adapters. So not a prototype. It's something that needs to live the entire life of the machine. Just once installed, you never want to think about this part again. You need something that's rigid. They're going to install brass inserts because brass inserts are a great way to add reliable threads to a 3D printed part. Usually model end threads are going to run into the geometry issues that you have from print, so whether it's coarseness or shrunk hole, and even post tapping may not be as reliable as just installing an insert and pressing that in. So I really recommend brass inserts for this. But the biggest thing was on this machine, they wanted to make sure that it was static dissipative. So they didn't want any charge buildup in this. We have a specific material called ABS ESD7 that is static dissipative, and it's great for this application when you're making panels that are on the shop floor, if you're making duct work, if you're making anything that's going to be around a dusty environment or where you're installing electronics. So even out in an ESD lab where you're doing some soldering and you need some fixturing trays, this is a great material, and one of the only materials in 3D printing that you can choose right now for static dissipation. So again, look at FDM. Over the list of these materials, you have many different materials that you can run boutique. So if you have a job where some parts require PCABS while other parts require ASA and green or blue, we can do that all under one order. But we're running these in boutique runs and multiple machines at one time. SLS and MJF are able to favor the many into one build, but it's limited in your material choices. So at Xometry, we have nylon 12 and glass fill, and glass fill is going to be a stiffer variant of nylon 12. But you can see that I've highlighted where my go-tos. Again, I like ESD7. Most of the time, that's going to be on a factory or some sort of assembly line. That's where I really like to use it. Polycarbonate, I mentioned before, the stiffness is great. I also love the color. It's almost like a bone china white to it. And I think it also behaves very well over large parts. So if I'm building a part that's 27 inches long in polycarbonate, I don't have too many worries about it flexing up on me. Where other processes, like for example, nylon 12, tends to misbehave when it gets that long because it tends to have internal stresses that are going to warp up on me. And then of course, SLS nylon 12 as that 85%. 85% of the time, this is going to be the right material to choose. As you scale up, look at multi-jet fusion, or say, for example, you do have more snap tabs and more flexible features. Multi-jet fusion may be the material to start with for this. So contrasting that, materials in photopolymers, SLA and polyjet. So let's start with polyjet here. Polyjet, you can configure the material to behave. So I could change that Shore value of the rubber-like prototypes from Shore A27 to Shore A40 by changing the internal digital matrix structure of the material. That's because it's actually made by jetting materials like an inkjet printer. So think like a color inkjet where you're depositing your reds, yellows, blues. In this case, you're actually depositing different materials or properties to edit the properties. You can do touch-like prototypes with this, so things that have multi-material. It's a great example of polyjet. It's also very quick, so it's something where you're usually looking at 2 days or less to shipping on your orders. Stereolithography has many engineering-grade materials, so these engineered materials are to mimic plastics, like I mentioned before. So you have something that maybe mimics polycarbonate, like I think this is Watershed here, or you have something that mimics like a general use ABS plastic. It's very good for prototyping right before injection molding. The accuracy of both polyjet and SLA are almost near CAD. So you're able to verify your CAD fit and function right before injection molding. It just doesn't necessarily have the long life that thermoplastics have. So understand that this usually has a shorter lifetime value to it, but it can be very valuable as you're using it for final validations. We've seen, over $100,000 of injection mold tooling be ordered, and they caught at the very last minute with an SLA prototype that there was a fit wrong, and that could have, that saved a tremendous expense on a change by doing a very, very low cost prototyping method. So just understand there's tremendous value to SLA because you're able to get those accurate fit checks. Of course, you have things like clarity and other other properties that you can do. So in this application example that I have on this slide, we had a customer, Narbox. They are going on their Gen 1 prototype, and they wanted something that had that form, fit, and feel. So it needed to be CAD accurate. It was a prototype, so it wasn't going to be, the snowboarder wasn't necessarily going to take it out and land on it in their back pocket. They wanted something that had a relatively smooth surface, and that overmold was so important to demonstrate. So can I have a rigid material with a rubber-like material molded around it? And I'm just very proud of these guys because they also got funded on Kickstarter. So you can see they had a successful raise, and I think they're actually on Gen 2. It's being sold on Amazon right now. But Narbox here, you can see that the rigid outer, so this is a rigid dark gray, and built at the same time on the PolyJet printer is a rubber-like outer shell. And this right here, you see the rubber-like outer, but it actually does have rigid inner supports to this. So this is actually a very cool overmold example where all you can touch and feel is rubber-like, but it actually had an internal structure. That's kind of the power of using multi-material 3D printing, is being able to simulate that. And honestly, once the CAD's ready, you're talking a couple of days, so it's very quick. It is more expensive than other processes, but it definitely serves that application purpose. So SLA, similar again when we think FDM, you have different materials to simulate different properties. I'm highlighting a few of them that I really like. ABS black has a nice jet black. It's very good for exactly what the name is, simulating injection mold ABS parts. Accurate Extreme Gray is my go-to. It's kind of a mixture of a ABS and polypropylene property. It's actually hard to classify, but it's a little bit more resilient with clip features as well as the white grain of it, where you know you can prototype very CAD accurate casings and get the results that you're looking for. Just understand that over time, you know, clips and other features can wear out or snap on you. And it's just kind of the nature of photopolymers is that happens over time. So it has a shorter term value than a thermoplastic may have. Some other cool materials that I wanted to bring up is Accurate Bluestone, which is that ceramic fill material. You know, I have specific applications that I've used that for. I've also seen people use it for custom tooling, even on the mold side. But it's just understand it is an extremely stiff material. Like if you should not expect any flex, and if you do try to flex it, it does snap. So it's very stiff. It's higher heat resistant than most of the materials. Just understand is there. Probably the beefiest material that we have is Somos Taurus. So that represents more like a nylon in its approach, and that's one of the newer chemistries that we've been working with. Polyjet, again, fewer materials, black, white, clear, and a rubber-like, but you're able to do this digital combination. So the value is in how you can combine those materials digitally. So metals, direct metal laser sintering, parts grow similar to what you see in stereolithography, where you have to have support structures to hold the part in place and these overhangs here. But just understand that these support structures are metal, so there's going to be some post-processing involved with this. It's great for making these functional design with complexity, design with purpose in mind parts. So it's a great surrogate for casting. It's a solution for metal prototyping, but really it comes with designing with DMLS in mind is going to be the highest use out of this. So the example that I have talking about DMLS is an example that where a fixture was needed, it needed to be metal, and for the life, it just, again, needed to be installed and moved on. The fixture itself has high amounts of complexity, which would make this more expensive for CNC machining. But because the Z height was relatively low and overall they did a good job at keeping material, the material was there to serve a purpose. There wasn't excess material to it. That this is a great example for DMLS aluminum. And that's what we ended up making this in for this customer. And these are parts that are in use on our product line every day. I'll also give a shout out in this picture. Looks like they were using probably ABS M30 black, or that this may be the ABS ESD. But they were also using, as part of the fixture, some FDM as well. But just understand, metal, it's fantastic. It is this is a fully dense metal. In fact, they actually, we've done studies where this is more dense than most state-of-the-art castings are. So if you're worried about porosity, this actually will give you a fully solid material. So just understand that it's a very, very strong material. The surface finish still has a powdery look because it's based in a metal powder bed, and that's how the outside of the part does fuse. But if you do cut into this material, so if you're doing any post machining to it, it will look like billet. So limited choices here. We're running aluminum alloy. It's very similar to a cast aluminum. We have our stainless steel variants, 17.4 and 316L. If you twist our application engineer's Tommy Lynch's arm, he may look into some other materials for you as well. So the last thing I have on this is, we've dug deep in different processes, different materials. Something to note is that this is still the Wild West. 3D printing, on these processes, they have individual machines. These machines have different build constraints to them. So just something to note is that if you have a part under 10 inches or about 9 inches or so, most processes can work for you. But the larger you get, the more it down selects. So for example, 9 to 12 inches, I may move you to or even like moving up to 24 inches, I may move you to a glass fill variant of SLS because I'm worried about some warping to it. SLA can build up to about 25 inches. FDM can go even larger. So if you're at 24 to 36 inches on your max extent, the only option I have for you to build a part in one piece without splitting and bonding is going to be fused deposition modeling. So sometimes when it comes down to it, you have a 30-inch piece. I may just say this is the process that we have to choose, and here's the list of materials that we have available. Let's talk applications and find what the best fit is. If you have something larger than that, I recommend sectioning the parts down. Sometimes you can section to go to that material that fits your application the best, or you could go to what gets you the least amount of parts. So for example, again, FDM, maybe you have a part that is, a 30, 30 by 40 inch part. And so maybe section that in two pieces so you can actually produce that in two prints. So please, 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 this is just the tip of the iceberg on what I was discussing today. There's so much that we could talk about. I've been talking over this for a decade now, and I'm still not done. So we have really great videos. I call it edutainment videos, where we're testing a certain property, and we're usually pitching a 3D printed material against a 3D printed material, like so SLS versus FDM versus PolyJet, for example. And so we have our will it melt, will it break, and other parts of this video series that we've done. We have design guides online for every single process that we offer. This is great to know the design nuances when you're making a part, especially for production in that given process. And we have case studies. In fact, a lot of these cases that I was talking about today are part of our case studies that we've been doing. And actually, Serena's been doing a great job of getting more on board. That's also my open pitch that if you are a customer and you have a great case, Serena is nodding her head vigorously right now. She's like, please send it my way, because all the work that we do at Xometry is confidential. So being able to share, it's usually like, for example, the supercharger, Rob reached out. He's like, I just realized it's been a year since I've had this supercharger in my car with no problems, and it was made out of SLS. And I'm like, this is awesome. Can I please tell people about this? He's like, sure. And I love these conversations. It's very exciting to see the applications on how parts and how different materials are working out for our customers. And honestly, you guys in some ways are more creative than us because you are the creators yourselves. So if you have any questions about Xometry in general, or you want to learn something more specific, our support line is the catch-all line. We'll get you to the right person. We have phone and live chat from 8 a.m. to 9 p.m. Eastern, Monday through Friday. We also have, of course, our FAQ, which answers a lot of questions for you. And Serena, we have a few promotions as well, right?
We do. Thank you, Greg. Thank you guys for sticking around to the end. Please use the code 3DSELECT to get $50 off your next 3D printing order of $100 or more. This is a one-time use code and expires at the end of July. We also have the Xometry referral program. If you're not ready to place an order now, go ahead and refer your colleague. The first time they submit a quote with their company email, they'll get $20, and you will as well.
All right, and that's what I have for today too. So I think we have a few questions I've been seeing queued up. So do you want to start going through some Q&A?
Yes, sure.
All right, you MC. I'll try to answer.
All right, sounds good, Greg. So with nylon, do you encounter issues with material swelling under liquid flow?
Ooh, that's actually a really good question, and I've tested that. So nylon does inherently have water absorption. In fact, actually, if I've been in injection molding for a little bit too. When you're shipping injection mold parts, sometimes you actually take a little spritzer of water to rehydrate the parts because the properties actually are better with a little bit of moisture to them. It doesn't mean they're naturally wet to the touch, but I think what you're talking about is, hey, I have a part that's going to live its entire life. So say it's like a basket filter that in my sewage treatment plant, it's going to live its entire life in liquids. Is it going to swell and go out of the geometry? Like, are my tolerances are they going to be messed up? What I have found is that the answer is not to any effect where it's going to be measurable. Like you may have some outer absorption. In fact, it will stain if you have something that has colors to it. And that, by the way, that's why we can dye nylon blue, green, yellow, red, is because that outer quarter millimeter of the material is slightly porous and it will take in a stain. But what you'll find is that if you cut into it, so say you just take a drill bit and drill into it, or take an X-Acto knife and cut on the side, beyond that 1/4 millimeter, it is solid plastic. Again, it looks like billet material. So my answer is nylon does have water absorption to it. You may find that a weight delta will be there if you are letting it soak in water and you take it out and let it dry for a little bit, but not fully dry in an oven, for example. But you probably will not find anything that will affect your overall tolerances for fit and function.
Great. So we have another question from Andre. What material would you recommend for extremely low temperatures?
All right. So I used to work in ruggedized military devices, and the extremely low temperature is usually a loaded question because I've done SLS nylon housings that have gone to that -40 to 140 requirement, but usually that requirement has a little caveat where it's for more like a cargo transportation. So I'm putting my device, my flashlight, in a box, and it's going on a C-130 somewhere in the world, and the C-130 does not have climate control, so make it -40, Fahrenheit or Celsius, it's the same temperature. But yeah, it's going to go below freezing, but it's not under a mechanical load. So if it's like a very low temperature and drop, then there may be a change to this question. But I've actually had success. I already gave away. I've had success with SLS nylon to that. But you're going to find a lot of these materials can get that low in temperature. It really has to do with what mechanical load or what mechanical property are you trying to demonstrate at that low temperature. I'm happy to help take that offline a little bit if you want to send me an email about your exact needs. But I can tell you that I've done testing with SLS nylon, and multi-jet fusion will act the same way, where it's able to get that low. And if I drop it, it's going to be stiffer. It's going to be below freezing, so it'll be more prone to snapping. But it still will thaw out and not have any overall problems to it.
Great. We have a question from Eric.
Mm-hmm.
He wants to know whether direct metal laser sintering printed stainless steel wire has the same resistance as a classic stainless steel wire, and the application would be for an internal ABS fishing hard bait wire for hooks link.
Okay, so you just got into the world of weird with powder bed processes. So overall, I was talking about the SLS nylon, that outer 1/4 millimeter. Although you don't see it in the data sheets, my experience has been that outer 1/4 millimeter of DMLS is where the weird properties are. It's something that has to do with you're scanning the material with a laser, and that laser is creating enough heat, generate enough heat to actually fuse the material that's hitting together, as well as fuse the layer underneath. But when you get up to an edge, it actually has to lower its laser power and kind of slow down a little bit. It's called end of vector. But the long short of that is that you have a different laser power and a different property, and you also have this splash of fusion where there's a little bit of thermal bleed that can happen, and all this is taken into account into this machine. So if you want something that's dimensionally tolerant, you're going to find that if you have a super thin feature like a wire, it's going to behave more brittle than a solid wire would, like something that's an extruded wire, just because the crystallization is very different on those outer edges, and the wire is not thick enough to give it the properties of billet like you get in most DMLS parts. So thinner parts, like very thin, like you're doing like a wall that's like 0.5 millimeters, are going to have a different material behavior versus like 0.5 millimeters of sheet metal when you're in DMLS, and it has everything to do with that end of vector and other internal parameters of that print. If you overheat it, so if you're working for GE Additive and you're trying to make that part work, and you're going to make 10,000 of them, then you'd actually be editing the parameters to basically just superheat that area and get the outer wall. It'll look a little worse, but it'll probably get you the properties you need.
And Greg, does that apply for titane as well?
For titanium?
Yes.
Yeah. So I will say it's the nature of the process itself. So it'll be inherent in the process of this laser powder bed fusion. This is important to note too. Like Xometry, what we're looking for is high repeatability. So we are using standardized methods like OEM parameters, OEM materials, OEM machines combined together to get a standardized output. So everything that I'm talking about is not in the research lab. It's something like if you uploaded your fishhook today, press order, you may actually get the fishhook, and it actually may be functional for you, but just understand that it will have a different property because it's so thin versus something that's truly formed or pressed out of wire, just inherent to the process.
Okay, we have a few more questions here.
Mm-hmm.
One more question we have. What 3D printing technology works best for modeling proto molds for short runs, specifically under 500 injection molded parts?
So if you're running a mold in-house, so say you have a low volume mold in-house, you're going to be looking for something that is heat resistant and stiff. My experience on that is somewhat limited. We've worked with thermoset materials. SLA and PolyJet both have thermoset materials that are useful for that. If you look at the heat deflection, it's actually much lower than the melted plastic. But because you're going to be actively cooling, like you're going to be keeping the air hose on that the entire time, it's not going to get to the point where it's going to deflect. Understand that if you have features that have, have a really deep pocket, you may actually want to CNC machine any internal cores that are going to create those features, because you're going to run into inherent roughness, or not inherent. You're going to actually break that part. So it's another tricky question. If you're building a soft material like a elastomer, or you're using it for a silicone mold, any of the thermoset materials, so any of the photopolymers, SLA or PolyJet, are going to work very well for you for that. But if you're running I'm doing thermoplastic injection molding, and I'm opening and closing, I may lean you towards just looking at actually getting a rapid mold made, like going towards actually using Xometry's injection mold service and having us do a rapid prototype mold, because it may be more effective and cost just about the same than experimenting with these photopolymers for it. The other materials, the reason why I don't mention the like FDM or SLS is it just requires so much manual post-processing, and it will be just a complete pain to get to the surface detail that you're looking for. I guess I should mention metals on that. We've had success working with mold shops where the mold shops have purchased net shapes of metals for custom inserts where they didn't want to do an EDM path, or hand-loaded cores where they then post-finish on their side. So again, that's an entire webinar in itself, but the short answer is, when you buy a part and expect to use it for an injection mold tool, understand you're buying a net shape, and then you're going to have to tweak it post-finish and expect to fail, on the get-go, because you're taking a material and trying to make it do something else. So you could build it at risk, and you can do that work, but just understand that it's more experimental than this is a set in stone rule. Here's your best practice.
So we have a few more questions. I do see we have some broad questions and we have some project-specific questions. I'm going to try and give Greg the more broad questions, and then if we don't get to your question that's more project-specific, please feel free to follow up with Greg through email or by phone. So this next question is, do you have any advice on silicone printing?
Silicone printing. So Carbon DLS has their SIL material. I haven't played with other than sample materials, but it is very promising for silicone printing. Silicone has been one of those newer achievements where it's been more exciting over the last few years. In the industry, what I look for, again, like putting on my Xometry hat, is something that is highly repeatable and has multiple providers. So we could use our Xometry network, and we're not putting all eggs in one basket. So if one provider goes down, say there's a storm in the area, that we don't shut down an entire product line. So from our side, I think looking at Carbon DLS is very enticing for me, because I do know that it has the decent amount of vendors, and it has a decent amount of repeatability. So it's something, it's something that's interesting. I've seen other technologies that are coming out, but none of them are hey, let's go, I have, $100 to spend on a silicone part. Let's go buy it right now. That availability is still not ready.
You mentioned, Greg, polyjet materials with softer durometer measurements, how they offer flexibility and squish, but not elasticity. What do you recommend if someone needs a soft elastic material?
So this goes back actually to the previous question. Some newer technologies are making elastomers that are much more functional. And I feel like a spokesperson for carbon DLS, but I'm very interested in that technology because of that. But if not, urethane casting is going to be the next best thing. So that's going to be a secondary process where you use a 3D print to make a master pattern, and then you actually create a silicone tool around that master pattern, cut out your part, that leaves you with a void in the shape of your part, and then you inject those rubber-like materials or those silicones and get those out. It's how I've traditionally done that in the past. It gets fantastic results for very low volumes. The other side of that is, of course, you can do low volume injection molding to go that way. So that bridge is, the technology is catching up for highly functional elastomers, and I'm very excited about that.
All right, next question here. Apologies if I butcher this a little bit. How small can you make a small pin diameter on a surface to increase surface area in material aluminum magnesium? Can you give the size in microns?
Okay. So that is, so anytime you ask how big or how small, it's a loaded question because a lot of times it's like over what length. So say I'm building something that is 0.5 millimeter wide, but 1 millimeter tall. So text is a good example for that. I can usually get away with that pretty well. You'll find aluminum is going to be have more kind of a rough edge on those small features, and that's because of thermal bleed. Where things that are have lower thermal conductivity, like stainless steel, the 17.4, will have a crisper feature in that. But just understand that if you're going over lengths, you're in the build environment, it is very difficult for some of those parts, like a stem or a pin, to survive. So it's something we have to look at the geometry itself on a case-by-case basis. But just understand, again, you're in the world of weird when you start getting that thin with those processes, and I may point you in another direction.
Okay, and another question from Eric: is there any opportunity to see future lead materials in DMLS?
So lead probably would be built using a different process than direct metal sintering. There are some other technologies out there, like binder jet metals, that it's not offered by Xometry, that will actually fuse metals together and then have some sort of post sinter to it. And I do know they've experimented with materials like tungsten for that, so you could have like some ultra dense materials. Like when I make carbide tools, right? So carbide tools are actually a compressed metal that is then post sintered in a furnace to get their properties. Actually, lead will be a little bit weird because of the property of the metal, but I have not seen anything on the marketplace that is hey, I could print lead right now.
And last question here, unless anyone else has any more questions from Charles. I have to print a prototype syringe part that will be subjected to centrifugal forces. What would be a good material to utilize? And it would need to be transparent as well.
So those SLA materials that we mentioned before, so I'm going to run back to my SLA. Watershed is a polycarbonate-like clear material that can work very well for those type of applications. So I would actually point you towards a SLA. The reason why I wouldn't say a polyjet clear, the clear material is actually great, but there's a support material over it, and when you have something like a syringe, sometimes cleaning out that support in those channels and features can actually lead to kind of some cosmetic marring on the parts. So I'd point you probably towards The polycarbonate-like clear materials like Watershed will bring you in the right direction, or Accurate 60. So Watershed and Accurate 60 are very similar in properties, and both are tried and true. They're some of the legends of SLA. They've been around for forever, so they can print very well. I'd also recommend on our drop-down selector to choose Strip and Ship as the or I think it's either that or it may become natural as the finish for it versus matte, because that's going to leave you essentially with how it's printed minus the support structures. So it'll give you a little bit more clarity from the get-go. Yeah, I think, guys, we are at time though. Any other questions that are submitted? I'm going to try to get back to you via email as soon as I can. But just really excited to talk about this. Again, if you have any more questions, feel free to email out. I'm happy to get you to the right resources or see if we can help answer on the fly for you. But it's always a pleasure to speak to you, and thank you so much for attending.